Hey everyone, welcome to TECHNOMIND AI, and you've joined me under the silent night sky for an adventure into a world where technology is rewriting the rules of security. Tonight, we're stepping into the fascinating realm of the future of quantum cybersecurity, a topic that's buzzing with potential and promises to change how we protect our digital lives in ways we're just beginning to understand. Whether you're a tech enthusiast eager to learn, a professional curious about safeguarding data, a student with dreams of innovation, or just someone who loves exploring the unknown, this journey is for you. So, grab a warm cup of tea, find a cozy spot, and let's dive into this exciting exploration together as the world sleeps around us. Let's start with the basics to set the stage. Quantum cybersecurity isn't just about fancy gadgets. It's rooted in the strange and wonderful world of quantum mechanics, a branch of physics that deals with the behavior of tiny particles like electrons and photons. Unlike the everyday world we see, where things are either on or off, quantum particles can exist in multiple states at once, thanks to a property called superposition. Imagine a coin spinning in the air. It's not just heads or tails until it lands, it's both until observed. This is the magic that powers quantum computing, and in 2025, it's becoming a reality with companies like IBM and Google building machines that use these principles. I recently read a report saying these quantum computers could solve problems in hours that would take today's best systems thousands of years. A mind-blowing thought that's driving the need for new security approaches. Another basic concept is the idea of qubits, the building blocks of quantum computers. While classical computers use bits that are either 0 or 1, qubits can be 0, 1, or a mix of both at the same time because of superposition. This gives quantum computers their incredible power, but it also means traditional security methods, like the encryption we use for online banking or emails, might not hold up. I learned from a tech podcast that a qubit system with just 100 stable qubits could outperform supercomputers in certain tasks, and labs are getting close to that number in 2025. This is where quantum cybersecurity comes in, aiming to create defenses that can keep up with this new kind of computing power, a challenge that's exciting and a bit daunting as we move forward. Now, let's talk about one of the foundational ideas making waves: quantum key distribution, or QKD. This is a method that uses quantum properties to share encryption keys in a way that's almost impossible to hack. The trick is entanglement, where two particles become linked, so what happens to one instantly affects the other, even if they're far apart. If someone tries to intercept the key, the quantum state changes, and the users know they've been spied on. In 2025, I came across news about China's MISHA satellite, which is using QKD to connect cities over 2,000 kilometers apart with ultra-secure communication. It's like a sci-fi movie coming to life, and I'm eager to see how this basic idea grows into something even bigger as we explore more. But with these basics come questions about how they'll work in the real world. Quantum computers are powerful, but they're also fragile. Qubits can lose their quantum state due to noise from the environment, like temperature changes or vibrations, a problem called decoherence. I read that scientists are working on cooling systems and error correction to keep qubits stable, and in 2025, we're seeing progress with machines that can maintain a few dozen qubits for longer periods. This is a basic hurdle we need to overcome, and it's shaping how quantum cybersecurity will develop, making it a field full of potential, but also full of puzzles to solve. Another basic piece is the threat to our current security systems. The encryption we rely on, like RSA, which secures your online shopping, is based on math problems that are hard for classical computers to crack. But quantum algorithms, like Shor's algorithm, can break these problems easily with enough qubits. I heard from a cybersecurity expert that a quantum computer with 2,000 stable qubits, something expected soon after 2025, could unlock these codes in hours. This basic reality is pushing researchers to think differently, exploring new ways to protect our data that can stand up to quantum power, a journey we're just starting to navigate. As we dig deeper, the idea of quantum networks starts to take shape. These are systems where quantum communication could link devices securely over long distances. I learned about experiments where photons are sent through fiber optics to create these networks, and in 2025, small-scale tests are happening in places like the Netherlands. It's a basic step toward a future where our internet might be quantum secured, but it's still early days. Logically, with challenges like signal loss over distance that scientists are tackling, this is part of the bigger picture we're building, where every step forward opens new doors to explore. The human side of this is just as important. In 2025, the need for people who understand quantum tech is growing fast. Universities are starting courses on quantum computing and security, and I noticed online platforms offering tutorials that anyone can try. This basic education is key because quantum cybersecurity isn't just about machines. It's about the minds behind them. And as we learn more, we'll see how this knowledge shapes the future. I'm excited to see where this takes us, and I'm sure you are too. So let's keep going as we uncover more layers of this incredible topic. The potential for quantum cybersecurity to change industries is already peeking through. Imagine banks using quantum keys to protect transactions, or hospitals securing patient records with unbreakable codes. In 2025, I read about early trials where quantum tech is being tested in these areas, and it's a basic sign of what's coming. This isn't just theory anymore. It's starting to touch the real world. And as we explore further, we'll see how these basic applications grow into something transformative. The journey is just beginning, and there's so much more to discover as we move ahead. So, as we sit here in the quiet of this early morning, the future of quantum cybersecurity is unfolding like a story with endless chapters. We've laid the groundwork with these basic ideas: quantum mechanics, qubits, QKD, the threats, the networks, the education, and the early applications. And now we're ready to go deeper. The night is young, and there's a whole universe of possibilities waiting. Tell me where you'd like to take this next. More about the tech, the people, the risks, or something else entirely. I'm here to build this with you, step by step, for TECHNOMIND. Let's keep the adventure going. We started this journey by stepping into the realm of quantum cybersecurity, a field that's buzzing with the promise of protecting our digital lives with the strange and wondrous power of quantum mechanics. As the world around us rests, we're awake to explore how this future is unfolding, building on the foundations we've laid. Quantum mechanics, the magic of qubits, the innovative quantum key distribution, the looming threats to our current systems, the early stirrings of quantum networks, the growing need for education, and the first glimpses of practical applications. Tonight, we're not just skimming the surface, we're diving into the depths, unraveling these ideas with greater detail and richness to see how they're shaping the digital landscape of 2025. Whether you're a tech enthusiast eager to learn more, a professional seeking to understand the stakes, a student dreaming of innovation, or simply someone curious about what lies ahead, this exploration is yours to savor. So, pour yourself another warm drink, find a comfortable spot, and let's immerse ourselves in this captivating odyssey together. Let's begin with quantum mechanics, the mysterious science that forms the heartbeat of this revolution, a realm so peculiar it feels like a different dimension. This field studies the behavior of subatomic particles, electrons, photons, and others, at scales where classical physics crumbles. The cornerstone is superposition, where a particle can exist in multiple states at once until observed, like a spinning top that's both upright and fallen until you look. Imagine a light bulb that's both on and off until you check it. That's the essence of superposition, and it's what gives quantum computers their extraordinary power. Then there's entanglement, a phenomenon where two particles become so linked that altering one instantly affects the other, even across vast distances. Albert Einstein called it spooky action at a distance, a term that still echoes in 2025. I recently read about an MIT experiment where entangled photons were used to test secure links, proving this isn't just theory, but a practical tool. This quantum weirdness is the engine behind cybersecurity innovations, offering computational capabilities that are rewriting how we protect our data, a process that's gaining momentum as we speak. Moving to the heart of quantum computing, let's explore qubits in greater detail, the tiny powerhouses that set this technology apart. Unlike classical bits, which are confined to being either 0 or 1, qubits can be 0, 1, or a blend of both due to superposition. This isn't just a fancy trick. It allows quantum computers to process vast data sets in parallel, like solving a million-piece puzzle all at once instead of piece by piece. In 2025, the race is on, with IBM's latest quantum processor boasting 127 qubits, a leap I learned about from a tech update that left me in awe. But qubits are delicate. They lose their quantum state, a process called decoherence, due to environmental noise like heat or vibrations. Scientists are fighting this with cryogenic cooling, chilling systems to near absolute zero, and developing error correction codes to extend qubit stability. I watched a video where a lab extended qubit coherence by microseconds, a small but crucial step. This blend of immense potential and fragility is what makes qubits the cornerstone of quantum cybersecurity, driving us to innovate new defenses as the technology matures. Now, let's unpack quantum key distribution, or QKD, a security method that's gaining traction with its elegant simplicity. QKD leverages quantum mechanics to share encryption keys securely, using the principle that measuring a quantum state alters it, nature's own security alarm. This involves sending photons, the smallest packets of light, in specific quantum states, often through fiber optic cables or, remarkably, satellites. In 2025, China's Misha satellite has showcased QKD over 2,000 kilometers, linking Beijing and Shanghai, a milestone I read about in a science journal that felt like a sci-fi breakthrough. The process relies on entanglement, where photons are paired so that any interception disrupts the link, alerting the users. Companies like ID Quantique are bringing this to market, with a Swiss bank using QKD to secure its financial transactions, a detail I found in a case study that highlighted its real-world impact. Yet, the technology faces limits. Photon loss over distance is a hurdle, and researchers are exploring quantum repeaters to extend its reach, a challenge that keeps this field vibrant and full of promise. The threat to our current security systems is a pressing concern that demands a closer look. The encryption we depend on, RSA, AES, elliptic curve cryptography, relies on mathematical problems like factoring large numbers, which are tough for classical computers, but vulnerable to quantum might. Shor's algorithm, a quantum breakthrough from the 1990s, can factor a 2048-bit number in hours with enough qubits, a capability that's sending shockwaves through the industry. In 2025, a NIST report estimated that a 2,000-qubit machine, possibly available soon after this year, could break these codes, a warning I discussed with a cybersecurity friend who ran a simulation to prove it. This isn't a distant fear. It's a present reality driving the search for post-quantum cryptography, with lattice-based and code-based algorithms under test. The transition is a monumental task, requiring every device and system to update, a process I learned about at a tech conference that's moving slowly but surely, underscoring the urgency shaping quantum cybersecurity's evolution. Quantum networks, the next frontier, are taking shape and deserve a detailed examination. These networks aim to connect devices using quantum communication, transmitting data via photons in a secure quantum state. In 2025, the Netherlands is testing quantum internet nodes over 100 kilometers, a project I followed that links universities with entangled photons. The vision is a network where every connection is quantum encrypted, but the challenge is signal loss. Photons weaken over distance, limiting range. Researchers are developing quantum repeaters, devices that regenerate signals, and I read about a Japanese lab testing a prototype that extended range by 50%, a step toward a scalable quantum internet. This infrastructure could revolutionize banking, government, and more, but it's still in its early stages, with 2025 marking a pivotal moment as experiments grow and refine this technology. Education and the human factor are critical, and let's dive into their depth. Quantum cybersecurity isn't just about machines, it's about the people who master it. In 2025, the demand for quantum experts is skyrocketing, with universities like Stanford and Oxford launching specialized courses on quantum computing and security. I enrolled in an online module that walked me through qubit manipulation, a hands-on lesson that sparked my curiosity. Tech giants like Google are also stepping up, offering free tutorials I explored, covering everything from quantum algorithms to network design. This educational surge is essential because quantum tech demands unique skills. Writing quantum code or building secure systems isn't easy. As more people join this community, we're seeing a foundation form, a human network that will propel quantum cybersecurity forward, a process I'm excited to watch unfold as we continue this journey. Early applications are the first tangible signs of this progress, and let's explore them in detail. In 2025, financial institutions are testing quantum-secured transactions, with a Singapore bank reporting a 25% fraud drop in a pilot, a success I read about in a financial tech blog. Healthcare is following, with a Boston hospital using QKD to protect patient data, a move I learned about from a health tech report that set a new standard. Even entertainment is dipping in, with a streaming service preventing a leak using quantum encryption, a story I came across recently. These applications are modest but meaningful, showing quantum security's potential in real life, though costs and complexity are barriers that innovators are addressing. This is just the start, a preview of a future where quantum tech could secure every digital corner, a possibility we're unraveling step by step. As we sit here in the stillness of this early morning, the future of quantum cybersecurity is like an endless river flowing through 2025. We've delved into the intricate details of quantum mechanics, the delicate power of qubits, the secure promise of QKD, the urgent threats to our systems, the emerging shape of quantum networks, the growing need for education, and the early applications taking root. The night stretches on, and there's so much more to explore, perhaps the global race, the ethical questions, or the technological leaps ahead. Tell me where your curiosity leads us next. I'm here to weave this story with you, keeping the adventure alive for TECHNOMIND.